Okay, do you remember we left off last week? We spent a little time talking, I think it might have been on Friday, it's been a little while ago, talking about what it meant to be a solution of an equation. I think we left off talking about what it meant to be a solution of a system. Does that make sense? Remember that? Maybe we'll just do a brief review. What if we've got something like this? Say I've just got a linear equation. What did we say it meant? Well, actually, here, tell you what, let's even go one step before that. What if I've got just a simple equation like this? Don't do that problem yet. Don't solve it yet, but just anticipate. Just tell me something about this. What's the solution going to look like? I don't care what the exact solution is, but just describe what it's going to look like.
One solution.
Okay, so start off. It would look like something equal what? X equals a number, right? Presumably. Okay. So it's going to look like x equals a number, and what is it, real quick?
3.
4. Okay, everybody agrees. We're going to add 1 and get 8 divided by 2. Okay, so we're going to get x equals 4. That is the solution. Remind me from our conversation, why is that the solution? How do you know it's the solution?
You can't do anything else to it.
True. I mean, that's the only answer we can get. You're right. How could how do we defend that that's what a solution means, though? What's special about 4?
Plug it in.
Okay, if I plug it in, what happens? Makes a statement true. Yeah. So remember what we said on Friday? It said, and we did talk about this, right?
Yeah.
A little bit. Okay, good. So if we plug 4 back in, it makes the equation true. In math, we say it satisfies the equation, makes it true. Okay, that's what a solution means in any situation in math. A solution is just a value of the one variable in this case, but maybe more than one variable, that makes the original statement, usually for us an equation, but it could be an inequality or something like that also, makes the original statement true, right? So if we look forward a little bit, what is the solution? Does it even make sense to say the solution? What does a solution to this equation look like? Remember what we did, didn't we just, what is that, by the way? That's an equation for what kind of a thing? Say it again.
Slope, like slope intercept.
Slope intercept, so that slope intercept is an equation for what kind of a thing? Is it
Linear.
line, okay, good. So it's a linear equation, or it's an equation for a line. And if I graph this, it's in slope intercept form. What's the slope?
3.
Which one is this? The slope 2 or 3?
3.
Now let's write down what slope intercept form is. Slope intercept form is y equals
And mx plus b.
mx plus b. And which one of those variables, m or b, is the slope always? M. Okay, so m is the slope, b is the y-intercept, right? So m is what in this case? Okay, and the y-intercept b is, okay, remember how we quickly sketch a line. Very simple to do. All we need are 2 points, right? We talked a little bit about that too, how 2 points define a line, right? If I have 2 points, I can just connect and extend. So I always need to just start with one anchor point and then create a second point. So what's the easy first point that I get here?
3.
Yeah, the y-intercept is at 3, right? So 1, 2, 3. So there's my y-intercept. How do I get a second point?
Just go 2 up and 1 to the right.
Okay, because of my slope triangle. If the slope is 2, same thing as 2 over 1. Slope is, we always say, is what over what? Slope is rise over run. So I'm going to go up by 2, and I'm going to go over by 1, and end up at this point right here. And so there's my line. Okay. Now this is the really important point that we left off with. Somebody, be brave, somebody tell me one solution of that linear equation based on the graph.
Good.
There are multiple.
There are multiple. In fact, there are an infinite number, aren't there? Somebody tell me one example of a solution. 5-1, okay? Because if I go, hold it, 5-1, you almost had it. But remember, when you tell me, you're telling me an ordered pair, that's good. The solutions are going to be in the form of an ordered pair because I need both an x and a y value, don't I? I have x's and y's in this equation. Which one comes first, though, in the ordered pair?
Y.
X.
Right.
X does, because, and think of it alphabetically. X comes before y, right? And so, and it's just alphabetical. So now, you say that again. You had it. At the right numbers. Starting at the origin, you were looking at that point right there, weren't you? How do you get there? You go over, the x value would be 1. There you go. So over 1 up 5. There's an example of a solution, isn't it? Because that's a point on the line, right? And it's also a value of x and y that if I plug them back in the equation, they make the equation true, don't they? If I plug in 1 for x, I get 2 times 1 plus 3 is 5. Well, that's the y value, isn't it? Right? So it works. Make sense? So there's two ways to look at that. There's kind of a graphical way. It's really, this is just, you're starting to get to a point in math now where you've done a lot of grunt work in the past. You've done a lot of stuff that really hasn't necessarily been so fun. But you've learned your math facts, you've learned some basic algebra stuff. But you're just starting to get to the point where math all of a sudden starts to become a little more interesting. Now it's things you can start to kind of see the relationships a little bit more. Here's just one brief example of that, where you can look at this in two completely different ways, but they're absolutely consistent. They just go together so well. This point, the values make the equation true, but if we graph the point, it corresponds to 1 point on the infinite number of points that we just string together to make that line, right? What's one other example of a solution? Yes, sir. 0, 3, absolutely. 0, 3, there's a point right there. And there are tons of other ones we could find. And there's all these other inconvenient ones in here that don't fall on nice integer numbers, but they're all there, aren't they? Right? So now what we're looking at today, though, today we're going to look at, this is just a single linear equation that represents all the infinite solutions of that single linear equation. Today we want to look at what happens if we take a system of more than one linear equation at the same time. Go away. There we go. Okay, so what if we add another equation here? Let's make this one a red one. What if we add the equation y equals negative x plus six. Let's graph that one. What's the slope?
-1.
-1, good, because the slope is the number in front of x. If there's just a negative sign there, that implies what number?
1.
-1, okay. So slope is -1, the y-intercept is 6. So we need our 2 points. Where's the anchor point? 6. So we're going to go up on the y-axis, 1, 2, 3, 4, 5, 6. So there's our first point. The slope tells us we're going to go
Down and right on.
good. This -1 is the same as -1/1, right? When we have a negative slope, we always want to put the negative number in the top. So the rise is what becomes negative. The run is always positive. Okay? So we're going to go down 1, over 1, and we end up right there. If I connect and extend, there's my other line. How many solutions are there on the red line? Infinite number. Okay, here's the question though. If I look at this linear system, the system of both equations at the same time, solutions to the linear system are trickier. They have to work for both equations at the same time. They have to simultaneously solve both equations. How many solutions are there that solve both of those two equations at the same time? 1. Where is it? At the intersection, right? So it's this point right here. What are the coordinates of that point? I think we already said.
1 and 6.
1 and 5.
Or 5.
Okay, for us to check that, I could plug it. We already checked it in the blue one, right? It worked. Okay, so are we done? We done checking it?
No.
It has to work in both, doesn't it? So we gotta check it in the red one also. If I put 1 in for x, I get -1 plus 6. Is that equal to 5? Yes, it is. So it works out. Okay. All right, so that's the topic of the day then. We're gonna look at how we can solve these systems of linear equations, of two linear equations. It's not always convenient to graph them though, is it? What if they hadn't intersected at a nice convenient place like that? What if they had intersected like right there? How would you know what the answer is from the graph? You couldn't really, could you? You can only know for sure if it's landing at a nice convenient spot, right? So we need a way to find those solutions analytically. In math, when we say analytically, we mean, using algebra, where we can get an exact answer. All right, so let's look at that. There's two different approaches to this. You might remember, and think back to last year. Remember talking about substitution to solve linear systems? What was the other one? Remember? Okay, substitution, that's what we're going to talk about today. Remember the other one? Elimination is what you called it. Okay, there's two. Sometimes you call it elimination. You might have called it, depending who your teacher was, you might have called it linear combination. Is that ringing a bell? Something like that. Well, anyway, we're going to review that. So if it's not strong in your mind, you don't have a real good recollection of how to do that, that's okay. We're going to spend some time reviewing it. Okay, let's look at first method. So there's two methods, substitution method and the linear combination method. The substitution method is the one that's convenient to use when it's really easy to isolate a variable in one of the two equations. In other words, if there's a variable in the system, either an x or a y, that has a coefficient of either 1 or -1, it's really easy to get by itself, and substitution is a good plan then. If you can't do that, linear combination is the other method. So substitution method, here's just a quick overview and then we'll look at some examples. We're going to solve one of the equations for one of the variables, the easiest one to isolate, and then we're going to substitute that variable into the other equation, okay? And then just do some algebra, solve. Okay, so we'll write the solution as an ordered pair. All right, so let's look at this one here. Now, before we jump into this, it's really important in math that you don't just hit the ground running. You always need to stare at the problem for a second and kind of think about it. Give your mind a chance to kind of work for you, and it does that, really. If you just let your brain kind of just focus on something for a second, it's going to come to a conclusion about how to proceed. It really will. What do you think here? Which of those variables is going to be the easiest to get by itself?
Top one.
We could do, yeah, and the bottom would work, wouldn't it? I mean, it would be easy to do, but there's a variable here that's even easier than that. In the top equation, which variable is really easy to isolate?
Y,
The y. How come?
because it's 1.
It's got a coefficient of -1 in this case, which makes things really simple, right? All I've got to do to get that y by itself is just either move the y to the other side or move all the other stuff to the other side, right? What do you think? What's your thinking on this? How would you get that y by itself?
Plus y minus 13.
Okay, most people don't say that. That's what I would do also. We have really two options here. We could, if we just take this top equation, let's just focus on this one for a second. If I start out with 3x minus y equals 13, option 1 might be, and this is the most common option, might be to say, okay, I've already got the y here. Let's push, and I want you to remember, I want you to think about this like pushing terms in this equation left or right. Think about it kind of visually. If I'm going to keep the y on the left, I would have to push the 3x to the right, wouldn't I? To the other side. How do I do that? How do I undo a 3x on this side?
Subtract it.
Subtract 3x? Does that make sense? So if I subtract 3x from both sides, those go away, and I get minus y equals negative 3x plus 13, because I'm just adding those, aren't I? Yes, ma'am.
Can you have a negative y in that equation?
Okay, now I'm not done yet, am I? I'd have to do something else, wouldn't I? I have to end up with just a y. So how do I undo the negative 1 that's being multiplied by the y? I could either divide by negative 1 or, that's fine, I could do that, but it's the same thing really as multiplying by negative 1. I think it's easier to think of it as multiplying. If you ever want to change all the signs in an equation, you just multiply both sides by negative 1, and all that really does is change all the signs, doesn't it? Right? So then we end up with y equals, now what am I going to get over here if I multiply, if I distribute a negative 1 through?
3x
Positive 3x
minus 13.
minus 13. Okay, so that took 2 steps, right? And it worked. We got our answer. But there's a quicker way. Watch this. We ended up having to change all the signs at the end, which wasn't too bad a thing, right? It wasn't horrible. But we can make this a little easier. What if instead, whoops, what if instead of keeping the y on the left, what if we push the y to the right where it's going to already be positive? Okay, how do I do that? Add y to both sides. And while I'm at it, my goal is to get the y by itself, right? So we could add y to both sides, and while I'm at it, if I want to get everything else to the left, what else could I do? Subtract 13. Make sense? Okay, what happened? Well, the y ends up over here, and the 13s cancel, and I end up with, whoops, there we go. And I end up with, over here, I've got my 3x that stayed here. The y's went away, minus 13. That make sense? To me, that's a lot quicker and easier. Just do it in one step. Push the y this way and push everything else that way. Okay? Does it matter that it's backwards?
No.
No, it doesn't make, it's an equation, right? I can put, each side is equal. I can put them in any order I want to. So I could just write this instead as y equals 3x minus 13 if I'd rather, right? Okay, that's good. I took the top equation and I isolated y. So now what? Let's see what the next step is. Okay, so there's our first step. I always say put a box around your substitution equation. Once you've isolated the one variable, put a box around it because you're going to come back to it, as you'll see. Now we substitute, right? So what's that mean? In the other equation, if I'm going to substitute this, what am I doing? I'm replacing the y in here with what?
With that equation?
Yeah, with all this stuff. The y is equal to the quantity 3x minus 13, right? So every place I used to have a y in the second equation, I'm now going to have the quantity 3x minus 13. Like this, right? Everybody see that? Everybody, that's kind of low. Can everybody see that okay? Right? So how many variables are in that equation? How many different kinds of variables? One. Only x's, right? If there's only a single kind of variable in an equation, we can always solve it, right? What are the steps we have to go through to solve this, though?
So the parentheses.
Go, I got to simplify it, don't I? I got to be able to get all the like terms together. So I'm going to distribute the 2. If I distribute the 2, I'm going to get what? 6x minus 26. Everybody agree? If I add up the like terms, then 2x plus 6x is 8x. Okay, now, and then they combine steps here. They added 26 to this side, which is good. Now I can point to a single variable. If I can point to a single variable in an equation, I can always solve for it by isolating it, reversing order of operations. Well, it's only one step here. What do I do? Divide by 8, and I get x equals 2. Okay, so that's half of the battle. I know what x is, right? I need an x and a y value. How do I find the y value?
You go back to your first substitution.
Okay, good, and that's why I put a box around it. Because now that I have the x equals 2, I'm just going to go right back to the box, and find out what y is by plugging in 2 for x. Make sense? Okay, so 3 times 2 minus 13, 6 minus 13 is what? -7. So my answer then is an ordered pair looks like that, right? The x value goes first. X is 2, y is -7. Okay. At what point would these two lines cross? 2, -7. Exactly. Okay. Good. All right, so moving on. Okay, I'm gonna skip linear combination. Yeah, I'm gonna skip linear combination. We don't need to do that one. Not today. Okay, what happens if you end up with? Let me give you another one. I'm just gonna make one up here. What if you have? Something like this. Say we have 2x minus y equals 8, and okay, try that one on your own. Try that one. Okay, so what happened?
No solution.
Okay, something weird happened here, didn't it? We probably solved for y in the top equation, right? Okay, it's easy to isolate. So what are the 2 steps to get that y by itself? Okay, good. We're going to push the y to the right, so we add y to both sides, and we subtract the 8 to the left. So would everybody agree then that I'm going to get up here, I'm going to get the y. Oh, it's on freeze. Oops. Okay, so I'm going to get, from this top equation, I'm going to get the y on that side, and over here I'm going to get 2x minus 8. Everybody agree? When I substitute that down here, I'm going to get my -6x plus 3 times all that, right? That's my new y. It's my substitution. Right? And if I distribute, I get -6x plus, come on, plus 6x, what do I get here? Well, what happens there? -6x plus 6x? 0. And I get the answer, -24 equals 9? When is that true?
Never.
Never. So we interpret that as no solution, right? So what does that probably mean about those 2 lines? How could you have 2 lines that never cross?
Parallel.
Parallel lines. There you go. Okay, now what if, I'm not going to take the time to do this, but what if we had done a problem just like this? And let's just say that our answer, when all the dust settled, let's say our answer was something like this. What if we get 6 equals 6? What would that mean?
Any solution.
Okay, that's always true, isn't it?
Yeah.
So what do you suppose that means? How many solutions are there to this one? Infinitely many solutions. How could that happen? 2 lines. They're the same line. Yeah, 2 lines are just right on top of each other, so they're the same line. Make sense? All right, so where are we at here? I still haven't got this schedule figured out. Hey, Ruby. Thank you.